this problem. Yeah, this one looks a little bit easy. Let me see. Let's try this one. I think this might be a little harder, but I'm not 100% sure. So we have triangle ABC. Okay, so I is the in-center of ABC. And then we have the orthocenter of BCI. So okay. Oh, I think I did this before. I forgot exactly how to do it. But yeah, I think I did this before. So that means I is the orthocenter of BCH. And then CD equals AB. Oh, actually, now I'm not sure if I did it. So we want to use our compass tool. CD equals AB and BE equals AC. Okay. Let me shrink the figure a little bit. Like that. CD equals AB and BE equals AC. And then we want the, well, that doesn't look right. Oh, maybe it should have, wait. I is the in-center, H is the orthocenter. Where did I go wrong here? Maybe I think the points are supposed to be on the other sides. Oh, A, D, and E lie on the same side of BC. That's the problem. So yeah. Okay. So I need to extend AB. Actually, that makes things a little easier, because then you draw the whole line. Actually, let me first delete that other ray. I want it like this. So we have this point, H. Well, actually, I want this to be D right there. Whoops. It's the wrong point. I want that one. Let me try one more time, then I'll move. There we go. Okay, so that's what it should look like. Okay, so I is the orthocenter of BHC, just as H is the orthocenter of BIC. It's like a symmetric relationship. So yeah, I like that picture. That's a good one. All right. Sorry, I see some people writing in the chat. AD, triangle center command. Okay, AD equals AE. I wonder if AH is perpendicular to DE. No, not necessarily. So it could be like this. Okay, but that's an interesting observation. So ADE is an isosceles triangle. Maybe it's worth drawing this point right here. So HI and F are collinear. I don't know if we want to hide this because we don't know it exists. All right, hold on one sec, guys. All right. All right. So let's see. What's a good way to do this? Could we use the reflection of the orthocenter? So does DE pass through some other nice point? Could be. Maybe. I wonder if BF is equal to CG. Let's check that. No, that's not true. Is DE parallel to AI? Yeah, DE is parallel to AI. Sorry. So yeah, what do we use about H? So if I reflect I over BC, then I would have a cyclic quadrilateral with H. So maybe I could use that somehow. I wonder if this is like Menelaus or something. We want to show EH and B are collinear. Yeah, what's a good way to do this? Oh, really? Interesting. So yeah, I think there's something with spiral similarities here. Like, because AD is equal to AE. Let me draw the circumcircle of ABC. Let's see. Yeah, AI is parallel to ED. That's true. All right. I wonder if this meets it at like the antipode of A. Oh yeah, it does meet it at the antipode of A because AE is equal to A, or I think it is. Let me check that that's actually true because I'm not sure actually. Sorry, let me move this. A, C, G. Oh no, that's not the antipode of A. Sorry. The spiral center of CD to BA. What just happened? Oh, sorry. That was weird. Okay, what's the spiral center from CD to BA? So how would you draw that? The midpoint of arc BAC. Ah, yeah, no, I think you're onto something with that. Let me draw the midpoint of arc BAC. Yeah, because I think that would give us a lot of congruent triangles. So is GA equal to GB? So we know GC equals GB, and we know CD equals AB. And yeah, so triangle GDC and GAB I think are congruent. And it looks like it also passed through E. So yeah, that gives us a lot of information. Yeah. Yeah, so I think you could use spiral similarities, or you could just use side angle side congruence, right? Because GC is equal to GB and CD is equal to AB, and then the angles are equal. So yeah, by side angle side congruence, those triangles are congruent, GDC and GAB. And then similarly, those are equal to GA. So G is the circumcenter of EAD. And since EAD is isosceles, you could draw that circle. Yeah. So we let G be the midpoint of arc BAC, and then it turns out G is the circumcenter of EAD. That's what we realized. Oops.
Well, actually, this problem isn't hard. I think I've figured it out.
Oh yeah?
So can you label the midpoint of BC?
Yeah, hold on just a second.
So we can easily prove that the reflection of H over M is actually the A-excenter.
Okay. So the reflection of H over M is the A-excenter.
Yeah.
All right. Let me draw that. All right. So is that a well-known fact?
I think it is enough to prove that.
It is true because A-excenter is antipode in BIC.
Okay.
So can you reflect E over M too? Same with D. We'll prove that their images are collinear.
If you reflect what?
Reflect E over M and reflect D over M.
Okay. Sorry. So reflect D over M. Sorry. This is
Yeah, and those three images should be collinear with A. We can prove that they lie on the angle bisector BAC really easy.
okay. So do we need point G for this proof?
Actually, yeah, no.
Okay. I'm going to delete it for now. All right, so we want to reflect E over M. Oh, I already did. It was just far away. Okay.
So we can see that BD prime is equal to CD, which is equal to AD. So we have angle BAD prime is equal to angle BD prime A.
Okay, hold on. So CD prime is equal to.
Actually, can you draw BD prime and AD prime?
1 second. DD prime.
No, yeah, DD prime and BD prime. BD prime.
A BD prime.
So and also AD prime.
Okay.
All right. So we have BD prime is equal to CD.
Okay. BD prime is equal to CD.
Is equal to AD.
Okay. All right.
So angle BAD is equal to angle BAD prime is equal to angle BD prime A.
Mm-hmm.
And because of the two parallel lines, we must have BD prime A is equal to D prime AC.
Okay. So basically, because this is an isosceles triangle, and BD prime is parallel to CD, then A, I, and D prime are collinear, is what you're saying.
Yeah, similarly, we can obtain that they are collinear.
Why is, okay. Why does H lie on AI, or why does H prime lie on AI?
Oh, H prime is the excenter.
Because it's the x-center.
Yeah, it is. We can prove that the reflection of H over M is the A-excenter.
Okay. Is that a well-known, that's probably a well-known fact, I'm guessing, right?
Actually, can yeah, I think it's well known.
Okay.
It's not really hard to prove. Maybe we can write it in the solution.
Okay. Yeah, let's write in the solution. So, okay, let D prime, E prime, and H prime be the reflections of D, E, and H over M. So I'm gonna fill in the details later for this, but okay, so H prime is the A-excenter. and thus lies on the A bisector. Oops. Oh, I forgot the dollar sign. And then D prime, we have BD prime equals CD equals BA. And so since BD prime is parallel to CD, that means that I'll say it this way. So angle BAD prime equals half of 180 minus angle B ABD prime. Which is equal to angle BAI. Which is equal to half of angle A. Yeah, I'll just say it this way, half of angle A. So this means that BI and B prime are collinear. And then similarly, or AI and B prime are collinear. And then actually, let me rewrite it this way. So D prime, E prime, and H prime all lie on the A bisector. A. And so and thus are collinear. So by symmetry, B, E, and H have to be collinear. All right. So then let's see if we could prove that fact. Okay, so in triangle IBC, the midpoint of BC is collinear with the antipode of I in IBC. Yes, and it's orthocenter. Yes, okay, I think I see what you're saying. So, because the orthocenter, the midpoint of the side, and the antipode of I are collinear. So yeah, that's actually, yeah, not that hard of a proof. So I could just write that. This is because in triangle IBC, the orthocenter midpoint of BC and antipode of I are collinear. So yeah, that's a well-known fact. I've done that a bunch of times on my channel. But yeah, that's a cool proof. I like it. So you weren't chosen for Vietnam PST. I'm sorry. But yeah, if they don't mind, make sure they don't mind sharing the problems, because I know some countries like want to keep the problems a secret. So don't yeah, get their permission. But yeah, I hope you make it. I'm not sure what year you are, but if you have another year in high school, hopefully you can make it next year.
Yeah, I'm only in 11th grade, so maybe next year.
Oh, what?
Yeah, I have one more year to try.
One more year.
Yeah.
All right. I hope you make it. So yeah, this one might be easy. After this, we could do some harder ones maybe. But yeah, these are all the problems I chose. So we could go back to that one that we didn't solve, or we could keep looking for some others. So M and N are the midpoints of those sides. And then the circle centered at M passing through B. Oh, M is the midpoint of AC. Actually, I think we did this problem before, but I'll do it again. I don't remember how I did it. Okay, so we draw those two circles. And I think he's from Vietnam. Yeah. So basically, oh, whoops, the centers of this, I didn't draw. This should be the circle centered at M through B. And the circle centered at N through C. And then we draw the point that makes this like an isosceles trapezoid. So I'm going to draw the circumcircle of ABC. And so yeah, we want to show that this point lies on the radical axis of the two circles. So this is point D. So yeah, we have this isosceles trapezoid, and we want to show D lies on the radical axis of those two circles. Let me make it smaller. So yeah, if I make it a taller triangle, maybe something like that. That's a good diagram. I just don't want to make that it look like the circles are like perpendicular. Although maybe they are. Is this line perpendicular to BC? I think it might be. Yeah, it looks like this line is perpendicular to BC. Is that obvious? Oh yeah, because MN is parallel to BC. So yeah, basically, since MN is parallel to BC, we know EF is going to be perpendicular to BC. And then it's just figuring out what So yeah, NC is equal to NE. And centered at N passing through C, and the circle centered at M passing through B. So MF is equal to MB, and NE is equal to NC. And we want to show, yeah, I wonder if we can use congruent triangles somehow. One second, guys, I'll be right back. All right. Vietnam likes geometry a lot. Yeah. Yeah, Vietnam has really good geometry problems. Okay, so MB is equal to MF and ME. Yeah, so maybe I drew more segments than I needed to, but okay. So yeah, how do I show, oh, first of all, I should call these P and Q, not E and F. This is P and this is Q. So yeah, I know PQ is perpendicular to BC. I can prove that, but I need to show that D lies on that. But yeah, I wonder if there's some congruent triangles that
I have a way to do this one, but it's a lot of, it's not really much, but we need to compute the power of point D.
Okay.
So we need to put a D value on the radical axis of the two circles, which is the power of D to the both circles are the same.
Okay.
So power of D, which respect to the circle M, is dm squared minus mc squared. So we need to prove that dm squared minus mb squared is equal to nd squared minus mc squared.
Okay.
And we can calculate nd squared by using this property that I wrote in the chat.
Okay, MD squared.
Yeah, because MD is the median line of ADC. We can calculate MD through AD, DC, and AC.
Okay. All right.
And B is the median of ABC, so we can calculate MD by using that formula that I wrote.
Okay, so we want to show D lies on the radical axis. So we take the difference between the powers. So like dn, so we want to show dn squared minus dm squared is the difference between the two radiuses squared. So we know bm and cn, and then dn and dm. How do we find dn squared and dm squared? Yeah, I guess that's my main question. How do we find dn squared and dm squared? So I know bm and cn, but I don't know those two.
dm
It's
square, dm is the median of ADC, so it can be calculated through AD, DC, and AC by the formula that I sent you.
Oh, because you're saying so dm is the median of ADC is what you're saying.
Yeah, so we can calculate it.
Okay, and then dn is the median of ADD. Oh, that's kind of nice. I kind of like that. So, okay, so all right. So yeah, there's a lot of like algebra in the solution, but it's not too bad. So I'll say let A, B, and C be the three sides. And then there's like a formula. So yeah, you put it in the chat. You can use it. You can prove it using Stewart's theorem, right? But so we have so I think it's bm squared is equal to half of a squared plus c squared minus a quarter b squared. I think that's right. Just have to write the other. Oh, sorry. Add that. I think that's right, right? Let me check the chat again. Yeah. And then we can say the same with cn squared. Half of a squared plus b squared minus a quarter c squared. Okay, so and then basically dm is a median of a dc. So we have dm squared is equal to half of AD squared plus, so CD is equal to AB, right? Quarter of B squared. And then since DC equals AB, and then similarly we have BN squared is half of AD squared plus, that's going to be B squared minus a quarter C squared. Oops. All right. And that's since BD equals AC. And so then from there we have BM squared minus DM squared. Or I'm sorry. So
I think it should be AD squared, not AD to the fourth power.
oh, sorry, you're right. Okay, so then we have dn squared minus cn squared equals dm squared minus bm squared. Or cn squared minus dm squared is equal to bm squared minus dm squared. So D has the same power with respect to omega B and omega C, so it lies on the radical axis. Their radical axis, and that implies D lies on PQ. All right, so that's the last step. Let me just check that this algebra works. So yeah, because this is A squared minus AB squared. Yeah. So yeah, a little more. Yeah, sometimes an algebraic approach is nice. I'm sure there's a synthetic way to do it, but I think this is kind of cool. You know, I don't do it that often, so I don't mind doing it every now and then. All right. So yeah, these problems were a little bit easier today. We still have the one we didn't solve, but if you guys want, we could try to find another problem. So this one actually looked kind of interesting. Let's see if we can do this one. I think this one looks kind of hard. So actually, I think they took this problem from another contest. So I'm going to go to the original page and cover it. Don't look at the solution because it's going to pop up. I should probably stop sharing my screen just so you guys don't see it. But yeah, don't look at it. There we go. So now I have covered it up. So this problem is with a 60-degree angle, 60 degrees triangle. So All right, so let's do that one. I think, I forgot what year this was. I think it's 2016. So, all right, so this is Baltic Way. So whenever I try to copy a less than sign, it doesn't work. So I have to, I don't know why this is, but I have to copy everything after the less than. And then I have to add it later. So silly. There we go. So AB less than AC. Okay, so this is, sorry about that. This is Baltic Way 2016. I think it's a short list, but I'm not sure. This might have actually been on the contest. So yeah, this is a 60-degree angle problem. It's usually an easy problem. Okay. All right, so I'm going to rotate this. Clockwise by 60 degrees. And I'm just going to pick a single point on it. So I'll call this point C, and then I'll hide everything. Okay, so all right, so actually, let me make this B and that C. Okay. And let me make it look more like this. Well, what just happened? It just changed. I want this to be C and this to be B. See if it works. Okay. Yeah, something like this. All right. And then we draw the three altitudes in the orthocenter. So AB, BE, and CF. K, L, and M are the midpoints of B, C, CA, and AB. Oops. Just trying to make it a little bigger. Now let me move A a little more this way. There we go. That looks good. All right. So this is K, L, and M. We want to show the midpoint of AH. So we have a bunch of midpoints. The midpoint of AH. Oops. This almost looks like a 9-point circle thing. AH, but it's not. DK, EL, and FM. So we want to show that those three midpoints lie on the same circle as I. So we have to use that 60-degree angle somewhere. Make it bigger. So we know, maybe I should draw the 9-point circle, because we know that yeah, I feel like this might just be the power ratio lemma. Wait, is that actually true? AH, that doesn't even look true. AH, am I missing something? I'm wondering if this is actually, because this doesn't look like it passes through N. Oh, I think it does. My bad. I was just looking at it wrong. Yeah. So this circle A for NIOJ. I wonder, is that the in circle? That almost looks like the in circle, doesn't it? Huh. I think it might be. Let me check that. If it's not the in circle, it's super duper close to being it. What if I moved around point B? Yeah, that, oh no, because here it's not the in circle. You can see it right there. Interesting. Okay, so yeah, it's not the in circle. So we would have two different circles passing through I. Are they tangent at I, or is there another intersection point? No, there is another intersection point. And it almost looks like that. Let's see. Yeah, let me draw the 9-point center. It's really close to the other one. Maybe it would be better if I made it more like this. Yeah, that looks better, I think. I wonder if there's something special about this point P. Yeah, it looks like P, Q, and J are collinear. Test that. Yeah, pretty sure that's true. How do we use that 60-degree angle? That's tricky. Is AI equal to AP? Looks like it. So if that's true, that although I'm not 100% sure that's true, but that would mean that Q lies on the angle bisector. G and Q look like they both lie on the angle bisector. So maybe that's obvious for the 9-point circle, because you would think. So AP passes through the circumcenter. Oh yeah, because they would be isogonal conjugates. So H and O are isogonal conjugates. Yeah. Oh, really? The circumcircle BHC passes through the center of ABC. So BHRC, is that a well-known fact? So yeah, it looks like AP and R are collinear. And then yeah, BHRC would be cyclic. That's what you're saying. And pass through G. Does it pass through G, or is that? I'm not sure if it does. It looks like it does. Yeah, I'm not sure the proof of all this stuff. AH is equal to AR because of the 60-degree angle. Okay, so I'm guessing that's like a well-known fact. Why is that easy to see, or there's like so I guess AH it's half the distance from R, or it's twice RK. Okay, because AH is equal to 2RK, and RK is half of BR, which is half of RA. Okay, so that makes sense. So AH is equal to AR, and H and R, let me call this O and rename the other O. I feel like that would make it easier. So I could name that R. I forgot what G is.
Maybe we can call G is the midpoint of arc OH of BHC, and then try to prove G is the center of the distances from G to the 4 points are equal.
Okay. So yeah, we want to show that G, the distance from G, yeah, so let G be the midpoint of arc OH. Okay. So I'm going to hide some stuff.
I think you should hide the circle passing through the 4 points, because you don't know that it exists in this.
Oh, this one?
No, I mean the circle that passes through the 4 midpoints. Because
oh yeah.
is external.
So does G lie on the, I don't think G lies on the perpendicular bisector of all of them, right? Yeah, because that's not a 90-degree angle. Well, wait, hold on a sec. Is G, yeah, well, let me, I just want to see what the center of that circle is before I erase it.
It's G. I think,
Oh.
yeah, it's G. We're trying to prove that G is the center.
Okay. Yeah, because yeah, GR isn't perpendicular. Sorry. Like GR, GJ, and GN aren't perpendicular, but it's still this, it's still true that we want to show it's the circumcenter. Yeah. Okay.
Is AR equal to AN?
Let's see. Yeah.
Is AM equals AE and AF equals AL?
Yeah, can you check if AM equals AE? Yeah, it is because of the 60-degree thing.
Yeah, so AM is AE and AF is AL.
And I think AR is AN too.
Yeah, so since they're midpoints, yeah, AR is equal to AN.
Yes.
So we can prove that GRE is equal to GN now.
Oh yeah, so then by symmetry, GR is equal to GN.
So we need the two other and prove that they are equal to each other.
So if we could show like GR is equal to GJ, that would solve it, right?
And also GI.
And also GI, yeah. Is G the, let me see. I'm just curious if G is like the in-center of ABC. That would be yeah, I think G might actually be the in-center of ABC. I'm not 100% sure though. It kind of looks like
Yeah,
it.
yeah. We can prove it
Okay.
because G is the intersection of AG and circumcircle BHC, and we can prove that angle BGC is equal to 90 degrees plus angle BAC over 2.
Ah,
Yeah, and that circle is how we define circumcircle BIC, which is which I is the incenter.
okay, so yeah, G is the in-center of ABC. So maybe that helps. All right, so GR is equal to GN. So yeah, G lies on the angle bisector. Then GR equals GJ. So basically that's saying, let's say I did draw that circle. That's saying that BR passes through like the other, wait, something doesn't look right. Because if G lies on the angle bisector, then if GR is equal to GJ, something looks weird. Like if GR equals GJ, wouldn't that mean this is like a kite? Either a kite or, yeah, I'm confused here. Or maybe either it's a kite or BJ equals BS. Yeah, I don't understand this. I'm a little confused. Like if GR equals GJ, wouldn't that mean, and G lies on the angle bisector, wouldn't that mean that GRBJ would be a kite? See what I'm saying?
Can you say it one more time? G or what?
So G lies on the angle bisector of ABC, right?
Yeah.
And we're trying to show that GR is equal to GJ, right?
Actually, R and J are the tangency point of the in-center, which is G.
No, I don't think that's true. So I don't think R and J are actually the tangency points in the end circle. So
Right? I think I just check it with GEO, GeoGebra.
yeah, so maybe I drew something wrong, but if I draw the end circle,
I think G doesn't lie on BOC.
G doesn't lie on BOC. Is that what you just said? But like the tangency point is like closer to here. So like let me see if I can. But like, yeah, I don't think it's tangent at R. I think there's like another point here. Sorry. Yeah, like it's tangent at this point, right? See what I'm saying?
Wait, so the midpoint of arc OH is really the center of that circle? Like, I'm afraid that we make a mistake.
Yeah, me too. Let me read the chat.
Because if G doesn't lie on that circle, then we
Yeah,
have been wrong. We should
I
have
think.
put it.
Yeah, let me check. So let's say I draw. Well, like it kind of makes it look like it. It kind of looks like it. So wait, angle BHC, we can calculate that, right? So if angle A is 60, then angle BHC, we can, what is that in terms of, okay, so that means these two angles add up to 120. So if we do 90 minus 1 plus 90 minus the other, And these two angles add up to 60. So yeah, angle BHC should be 120. Yeah, I could just use this, right? So BHC is 120 and BGC. Oh my goodness, that's so close. 119.68. Is that really? Yeah, it's not 120. It's very, very close, but it's not 120. Wow. Wait, how could it be that close, but not? Okay, so these two should add up to 120. So half of them should add up to 60. Oh, it depends on how you're defining. So G is not, if we define G to be the midpoint of this arc, yeah, no, G is not, yeah, we kind of messed up. So I think G lies on the circle, but G is not the in-center. So our S and G, yeah. So if I do, okay, I'm very confused here. Yeah, S and G I think are not the same points. So there's the in-center and then there's the center of that circle. They're not the same point. They're really close though.
So we must approach another way. We cannot just call that point GL and prove that it is the center.
Yeah. Whoops, sorry. But I think G is still the, like G is still the center of the circle. It's just not the in-center, I think, right? This almost, does this circle even pass through I? It almost doesn't look like it. Wait, this makes it look like these 2 points are the intersections of the circles. Okay, I'm confused here. This makes it look like the problem isn't true. It's like this circle doesn't actually. Oh, that's because I drew the end circle. I don't want the end circle. I want. I want this circle. Here we go. That's the circle we want to show exists. So yeah, this circle we have to remove. So BHOC is cyclic, but BHGC isn't necessarily cyclic. Yeah. Okay. Okay. Thanks for joining, though. I appreciate it. Have a good one. All right, let's see what I can figure out here. We have 20 more minutes. Yeah, this one feels so hard. I think this one was like a G13 for Baltic Way. So it's going to be pretty hard. You don't think it's that hard? Okay. Yeah, okay. Well, let's see. Oh, yeah. So what's a good way to show this? So Q is the 9-point center. So we know that these three are perpendicular. So basically, maybe it's worth drawing the isogonal conjugate of Q. Or so Q is the 9-point center. And okay. See you next time. Have a good one. So just me and you, Blue Hawaii. How about, so BHOC is cyclic. We know that. I'm not sure how much that helps us. Yeah, this one is hard. How about okay, so what does that mean? So basically I lies on the 9-point circle, but then if we take all the midpoints, it also lies on a circle. So what does that mean? And it looks like J, Q, and P are collinear. So what if, so I start with a 9-point circle. And then I draw the perpendicular through J. To BC. So J is the midpoint of BK. Yeah, where's the 9-point center? Yeah, Q is the 9-point center. So yeah, maybe first I could show JRPN is cyclic. And then once I show JRPN is cyclic, then I could show JRIN is cyclic. Okay, so basically I'm going to hide this circle. How could we show JRPN as cyclic? So first of all, is it obvious? Is it obvious that P lies on the 9-point circle? So let me write out some stuff here. So let the perpendicular bisector of JK meet AO at P. All right. So first, can I show that P lies on the 9-point circle? So the radius of the 9-point circle is half the circumcircle. So basically I want to show that QP is half of the radius of the circumcircle, which is OA. So QP is equal to OP is basically what I want to show. Which is kind of the same as saying angle AQO is 90. Oh, you know what? I think that's obvious because AH is equal to AO. So AH, yeah. So we have AH is equal to 2OK, which is equal to OB, which is equal to OA. And so okay, so I'll say let Q be the 9-point center of ABC. So the midpoint of OH. Okay, so we have that. So that means angle AQO is 90, which means that PQ equals QO. All right. Okay, so we have QP equals I think we can show that P lies on this circle. Then we could try to show that PRJN is cyclic. And then once we show P lies on it, then we could try to show I lies on it. Okay. So check this. Okay, that's not a right angle. So if we want to show that that's cyclic, so we could try to show angle RPJ is, I want to show PRJN is cyclic. Can we show angle RPJ as angle RNJ? So angle RPJ maybe there's a better way. Yeah. Yeah, we just have a couple minutes left. But yeah. I want to show that PRJN is cyclic. Let me draw that circle again. Let's see, how would I do that? I could use power of a point. I could try to do an angle chase. I feel like an angle chase is probably the best way to do that. Because so R and N are reflections across the angle bisector. So I think we should be able to use that. So angle PRN is ARN minus ARP. I wonder if there's a way to calculate angle RNJ. I wonder also, let me check. We have some cyclic quadrilaterals here. So all right, we're almost out of time, so I think I'm gonna stop here. So for everyone watching on YouTube, thank you, and thanks to all the participants that joined on this session. So yeah, it was a lot of fun, and the problems were a little bit easier this time, but this last one was surprisingly tricky. So if you can find the solution to it, I'd be happy to hear it. I also wanted to give a shout out again to the chefs of problem solving. So first of all, I want to thank the guy that created the YouTube channel. I think it's a fantastic channel. And I like how he goes really in depth into all the different solutions he gives. And for any of you interested, I'd highly recommend his Chef Scholars program. So it looks really fun. I think he's currently in the application process. And I've heard that some of the problems in applications are pretty difficult. So if you're into Olympiad GEO and you're at a certain level and you want to take it to the next level, definitely recommend his program. All right, so thanks for watching. If you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. My email is in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. So thanks for watching and have a great day.